today, and it includes our invited talk, and it's my great pleasure and honor also to introduce Manuel Hermenegildo. And I should start by mentioning that he's an ACM fellow. He was elected last year, and this is an award for the top 1% of ACM members, and awarded by nomination to people who distinguish themselves both in their research achievements and in their contributions to the computer science community. And I have no doubt that Manuel qualified adequately, more than adequately, in both counts. So for the last 30 years, after obtaining his PhD from University of Texas at Austin, he's been a leading figure in logic programming, constraint logic programming, parallel programming, program analysis and transformation, programming environments, and program development environments. And he's a professor at Technical University of Madrid, and also the founding director of IDEs Software Institute, which he built up into a world-leading research institute in the 10 years that he was the director. Now, I could go on, but I decided to ask for expert opinion in introducing him. So I asked ChatGPT to write me a little poem, and it generated 6 rather poor verses, but actually a couple of them captured very nicely some of what I wanted to say. So one verse is: a mentor, a guide, a visionary mind, to his students a beacon forever kind. In the world of algorithms, he's a luminary star, a famous professor, revered near and far. From Prologue's mysteries to AI's grand design, in algorithms and data, he's a paradigm. That doesn't really rhyme, but a mentor, a scholar, in his wisdom we confide, for he leads us on the path where brilliance does reside. So with that, I would like to introduce, I think Manuel's talk will focus, or at least the themes of program development environments and analysis of programs will be in the fore in his talk, which is entitled On-the-Fly Verification via Incremental Interactive Abstract Interpretation with CiaoPP and VeriFly. So, Manuel, over to you.
Well, thanks very much, John, and thanks very much, ChatGPT, of course, for giving us such a hilarious contribution. That's a lot of fun. Okay, so on-the-fly verification, that's the objective. It's work done with Isabel, Jose, Pedro, Louis, Daniela, and Daniel, some of which Pedro and Jose and Daniel are here. And it's a real honor. Thank you very much for inviting me to give this talk. Hope I can present some fun stuff to you. It will be a little bit of slides and then some demo. I mean, for the fun factor. So the objective is to analyze and verify software projects interactively during development. What for? To detect bugs, to verify assertions, and to do this on the fly in the editor. Of course, you can also do it at commits and so on, but the concentration here is to do it in while you're editing the program. And the problem, of course, that you have is that the precision that you need to be able to do significant verification and to get significant results, which typically requires context sensitivity, complex domains, and so on, can be quite expensive. No? So we address these issues in our tool with several techniques, and I'll try to talk about some of those. The first one is to have an efficient context and path sensitive fixed point, the top-down algorithm of the Ply analyzer. I'll talk a little bit about that. So this, start with an efficient analyzer that has the precision and can get this precision efficiently. Incrementality, fine-grained incrementality. But our work on incrementality was originally not exploiting the module structure. Then something that we've done more recently, all the other stuff is relatively old work, very old work. What we've done more recently is to combine modular analysis with incrementality, which is what you need to really scale and do this, make this a reality, and the IDE integration, which is the fun part, which I'll try to show. We try to do this, well, you know, we're Prolog people, we love Prolog, we do it for Prolog, but we also support other languages via translation to constraint horn clauses, also known as Prolog or CiaoPP. And we try to cover in this verification objectives, covered both functional and non-functional properties, so types, pointers, aliasing from pointers, shapes, recursive data structures, things like intervals or you know, numerical domains and so on also, and then the non-functional properties like time, memory, energy, gas, etc. Now, how did we start? A bit of going back to the beginning, which also because we're in LOPSTR and people are familiar with this. In the 90s, mostly languages were mostly statically typed, you know, and that was the religion, let's say. You know, we had ML and Haskell, and in the logic program, that from the functional programming side and the logic programming side, we had Gödel and Mercury. And in that context, a bit also in the view of Mercury, of how Mercury was and the things that it had to give up from the traditional logic programming to achieve the goal of verification, we developed the Ciao language, Ciao Prolog language. The idea was to provide, of course, a very good Prolog. You know, you know, that's our main objective, but in addition, so it's a Prolog that has extra stuff, and the main thing is that we try to provide the flexibility and the fast prototyping of a dynamic language, as we love, and somehow to also give the guarantees of the strongly and static and strongly typed languages. So somehow our objective with this system and with what we've been doing for all these years is to bridge the gap between dynamic and static languages. In that sense, I mean, probably, I think that Ciao Prolog was the first dynamic language with safety assurances, so something that is now very popular if you think of, I don't know, TypeScript or all the additions that they are doing to Python and so on. Is sort of the same idea. What are the keys of the approach? The first one is to have assertions rather than strong types or traditional types. Types have evolved, of course, and we can talk about that in the questions maybe, but you know, to have assertions, have the assertions be optional, to not restrict the properties that you can talk about in the assertions, and therefore accept undecidability. Your type system, your inference system, your abstract interpreter has to deal with undecidable properties, and that takes us, of course, to having to deal with approximations, but safe approximations, and that leads us to abstract interpretation-based verification. So the idea of abstract interpretation-based verification, we wrote a very early paper on this, is that you can, all your tasks from verification, like determining correctness, completeness, incorrectness, and incompleteness, so verifying and finding bugs, can also, thanks to very good ideas from John, can you know, phrase in terms of comparing your intended semantics with abstractions or of your intended semantics in an abstract domain with abstractions of the concrete semantics, and developing sufficient conditions for this verification. This is not to go into this, but now to be able to do this, to be able to have an approximation, an over approximation, sorry, or an exact approximation or an under approximation of the meaning of programs, you need an analyzer, and for that we developed, actually was motivated by parallelizing programs, but we had it, a framework for program analysis for abstract interpretation, which basically takes a set of horn clauses, constraint horn clauses, and some abstract domains, and calculates a safe approximation to the meaning of the program in this abstraction. The algorithm is essentially an efficient, incremental, abstract OLDT resolution. So it's a resolution algorithm with tabling. It's sort of the original top-down algorithm. I think we came up with this algorithm, and it's pretty much, it's the algorithm used in many analyzers nowadays. And the components are, one of the main components is that make it efficient is first using memoing, to using a call answer table where you store multiple entries for each block. You store the call pattern and the success pattern, and you store several call and success patterns per block, where the success patterns or the exit states are are they abstract the exit states for a particular entry state into the block. And or if you want to think about it as preconditions and postconditions. And this is probably what we would call now summaries, for example, if you have several of them and so on. And then you have a dependency arc table, very important, that basically links these table entries so that you link the answers for a call A to the answers of a call B, so that you know that if the exit for a call B changes, then A will also change. And therefore you track dependencies in this way. This gives you context and path sensitivity. Path sensitivity because this dependency arc table, these links basically abstract the paths to the program. They abstract them as regular structures, or as grammars. And then you get multivariance. You can have several versions of procedures or blocks. You get program point info because each one of these call answer tables corresponds to program points. You get efficiency because of the memoization and also because of the dependency tracking, because this dependency tracking allows you to optimize the fixed point and converge much faster. You also construct the strongly connected components on the fly, take advantage of the base cases and so on. You have genericity in the sense that the abstract domains are plugins, and also the widenings, for example. And of course, it handles mutually recursive methods, library calls, externals, and so on. You can guide it with assertions, so there's a mechanism for saying when it loses precision to provide information to guide it. And it works with modular, and now, well, it used to work with modular programs and with incrementally, and lately we've managed to combine these two things, which is what I want to talk about. Okay, so the analyzer basically takes a source program, just a set of constraint clauses, having constraint horn clauses. It analyzes and it gets some information, which is true information. We call them true assertions. So that's what comes out of the analysis, true assertions. And this can be recursive types or shades, pointer aliasing, as I said before, constraints, and things like determinacy, non-failure, cost, sizes, termination, anything like that. Then that information is compared to the assertions, to what we want to prove. This can happen as a separate process or inside the static analyzer, it doesn't matter, but we depict it here separately for clarity. And the result of that can be that the assertion is checked, and then you have verified the assertion, and you also have a proof. This is very important. I mean, so you get a proof that the assertion is false, and then you have found an error statically, all this is static, or, and this is what non-desirability brings you, you may not be able to prove it, and you have to live with that. Now, what do you do in those cases? Well, in our approach, when you have an assertion that does not, you cannot prove it at compile time, you cannot prove it statically, then we turn it into a runtime test. So at least we get dynamic safety. What's maybe called dynamic verification nowadays. So, and now this is important for this to work, for the fact that your assertions can be checked at runtime, your assertions have to be runnable. Now most systems either have runnable assertions but they are not checked at compile time, like in C, the asserts in C and so on, or more traditional systems, I should say. Or you have assertions that are proved by theorem prover statically but have nothing to do with runtime. Of course, these things have evolved, and now we have dependent types, and we have all these things. But this is the original model, no? And but of course, then for that to work, your runtime, your properties that appear in assertions have to be runnable, so that you can actually check them also at runtime. So I'll talk about that in the demo. So this is something that we proposed, as I said, in the mid-90s, and it's a true precursor of all the gradual and hybrid typing approaches that we have nowadays. Now, the other aspect, that is that in order to support different source languages, we propose to do translation into horn clauses. So the idea is that you take, if the source language is in a different, the source program is in a different language, then you translate it to horn clauses. This is what we mean by this, the check, false, and check. This is an example, a very quick example of a filter. This is a filter from from a company actually, from XMOS. And here we have a pragma that says we want to check some energy consumption. And then this is exactly the assertion that goes into the static checker, and that we combine with the true information, which is this one, that comes out of the analyzer. That tells us that the actual energy consumption is larger than 3.35 times elements. Elements is an input parameter here of the program, plus whatever, and this. So it's between this upper and lower bound. And then when we do the check, we end up getting two of these results, because you can get multiple results. So you get, thanks to a great idea from Pedro, to divide this into by segments, intervals. So you get parts, values of elements for which the assertion is checked, and values of elements for which the assertion is false. So anyway, this is to put more in perspective the idea of how it works and how it works on this is an imperative program, and actually the analysis is done of a property that is energy is done on the machine code. But anyway, having said that, we go back to the model, and the next step is incremental analysis. So incremental analysis is, the change, as you can see here, is that now we have several versions of the code. We have version 1, version 2, version 3, and as we change versions, we take snapshots of these program sources. This can be at each pause, while editing, each save, each commit. For example, in the integration system and the continuous integration system. And these differences, these increments of constraint horn clauses, it doesn't matter, the source language doesn't matter. In the end, there is expressed in an incremental change in the horn clauses, are detected with respect to, with the previous snapshot, and then we reanalyze. We annotate and remove potentially outdated information. We reanalyze incrementally only the parts needed, module by module, until an intermodular fixed point is reached again. And then we recheck and optimize. To see a bit how this looks, this is a real analysis graph from a small application that has a planner. It has 3 modules, a planner, a small user interface module, and it uses a library, which is not too much of a library, as you can see, but it's some part of our library. And now let's assume that there's some change here, that there's been some additions to the library, and there's some deletions in the planner, in the main program. We have added something here, and we have deleted something there. Now, for example, we concentrate on module, and we see that there was an addition, so there's some computation here, so we add some part of the graph, and this creates new call patterns back into the planner, new returns, new exits, which in turn produce new call patterns there. And then the deletion eliminates part of the graph, trying to eliminate a minimal part of the graph, and then recomputes after that elimination, and maybe creates other new parts of the graph that are generated after that elimination. As I said, the algorithm maintains local and global graphs with call success pairs. These should be really tables, local and global tables with call success pairs for the predicates and their dependencies. So we have the local tables in each module, and then we have the tables at the interfaces, which is how the modules communicate. And this is incrementally with additions, deletions, and the idea, of course, is to localize the fixed point as much as possible inside the modules to minimize the context swaps. All right, so we have some results here, but I will, just summarize them for the sake of the talk. In just saying that, the process, the modular incremental process has guarantees. It will provide a correct approximation, so it's correct, so a correct over approximation of the semantics, even if we're using widening. But if we want to get the exact same least fixed point that we get if we analyze just one module without incrementality, we do have some conditions on the widening. The idea is that if you, this is something that other people have also realized later, that if you have a widening, because the widening is kind of a bit arbitrary, right? It will depend on the order in which you process the modules will affect the order in which you apply the widening, and therefore you can get other more general results. Always correct, but maybe not the least fixed point. So you have to put some conditions on the widening which are in the paper to get this to work. I mean, if you're interested in getting the exact same least fixed point, which you may not. I mean, anyway, and then we have we got some pretty interesting results also for reanalyzing starting from a partial analysis. You have an analysis that has stopped without being completed and you want to restart it after changes, that it also works. The algorithm also works for that, which is very useful if, for example, you're editing and you're changing things while you're editing and it hasn't quite finished the analysis yet, so it can resume from partial analysis situations. Some experimental results, I'll just give an idea because it's better to just go through some examples. So the speed up is really unbounded, the speed up of, if you do modular analysis, you can have 1 million modules and only make a small change, so you can just make it, depending on the benchmark. But for a set of benchmarks, we were seeing order of magnitude speed up of incrementality with respect to not being incremental, and modular incremental getting even more speed up, about twice or so with respect to non-modular. And also we managed to accelerate modular analysis from scratch, but that's really a detail. All right, so we saw verification, we saw incremental verification, incremental analysis, incremental verification. So the next step for our system, of course, is to add the interactivity. This is more engineering, than science, but it's it's fun. So the idea is that we add in the integrated development environment some support for communicating with the analyzer. So the idea is that the IDE can calculate easily. So we normally in the incremental analysis we calculate the differences inside the analyzer, but the IDE can also very efficiently calculate difference, because it's editing the program. So maybe you get that, sometimes we get the difference directly from the IDE, from the editor, or the environment, the development environment, and that is what's fed here. And of course, the idea is that whatever results you get, be it for the compile time checking or even from the runtime checking, are reflected back on the source program in the IDE, which is something that we have done for a while, for like syntax errors and so on, but the idea here is to elevate it to a different level. We have made an interface with Emacs by extending flight check, which is what most of us use. We also have a browser version that I'll try to show, where everything is running inside the browser via compilation to WASM. With a VeriFly, VeriFly is the name we've given. It's a funny name, no? It's a VeriFly, verifying on the fly. So it's a verification on the fly, the VeriFly system or the VeriFly approach. But you can do it for any IDE. For example, we have a version now also for Virtual Studio Code. All right, and so I think with this, I can maybe do a little bit of demo, show some things, hopefully fun. So some very basic stuff first, for those that have not seen this system before. I'm going to basically take this out, and I have here, this is just plain Prolog. I have a predicate that defines 3 colors, red, green, and blue. Of course, if I load this predicate, let me do it in a different way that is better. Load it like this. There. And I call color, this Prolog, right? So, I get red, green, blue. Now this looks awfully like a type, right? So in Ciao, this can be a type. The only thing needs to be a type is to be declared that it's a type. Actually, a type is just a special kind of prop. So in general, props are things that you can use in assertions that I will be able later to use in an assertion, like here. I can use color here in an assertion. So if I declare something as a prop, then it's something that I can use in an assertion. It has to meet certain conditions so that it can be used as a runtime test and also so that the analyzer can understand it. And then a particular case of prop is a reg type, a regular type, which I can write because I loaded the reg types library, and I could write prop because I loaded the assertions library. All right, so now nothing has changed. You know, if I do this, I'm still, you know, I do that. And then the cool thing is that now I have this predicate, you know, which of course is predicate that returns red, no, that's obvious. And if I just comment this out, then the system on the fly, hopefully, if it wants to do it, let me put it here on top. Okay, there. And start again. Okay, I know, okay. Okay, it's giving me the error there, but I mean, there. So it just said that it has verified the assertion, the QX assertion. So basically, it's taking this as a property, and here what I'm saying is that predicate Q of X, when it exits, X will have the property color, and that gets checked statically as you saw. Now I can do a little bit nicer, and I'm going to, because I loaded the functional syntax library, I can write predicates like this. So when I put colon equals, that means that let me just do something real quick. If I have P of AB, I can also, in the functional syntax, I can write also this like this. These two things are exactly the same thing. So it's just syntactic sugar to write in functional syntax. You know, so I take the last argument and I make it special and I mark it behind the equal dash. So it's the only thing. But that allows me to write this like that. Right, and then write this. Whoops. Like that. Which of course still works because it's exactly the same program as before. It's exactly the same thing, no? And then I have more syntactic sugar. I can do this and OR. And now I get a nice type-looking thing. Yeah?
So in order to be declared as a function, you do not need it to be a function.
No, in fact, you see.
It's a non-deterministic function.
Exactly, it's just syntactic sugar, and we love it like that. What we like is the syntax, not the semantics. The semantics you can have, but it's very simple. You put an assertion. You want a function, okay? So you put an assertion. You say that all the inputs are ground. The last argument is a variable, and it's deterministic. And now you have a function. In fact, we have a macro func that does that, but it's on top. To be a real function is a restriction on top of predicates. Yep. So you see, this still working. You know, and it's still verifying. No. See, it says here it has checked the success of Q. Okay, so now, just for fun. I mean, we're here to have fun. So this is a bit more interesting. So color list, of course, this is, let me write it first, and then we'll do parametric and everything, okay. So if I can do color list like that, I'm first going to write it in Prolog. So color list would be something like this. It's either nil or X, head, tail, right? Where H is a color, right? And T is a color list, right? So this is my color list. Of course, if I run it, I can check if something is a color list. So this is very important that you can run your properties because they have to be runtime tests because they may be undecidable. It all has to match. Okay, and then of course we have this very nice thing that we can explore types. Now, of course, we look at like this and it looks a bit ugly, the enumeration, because of course we do depth first. Easy to fix. Well, before I fix that, let me just fix the syntax. I can, of course, I'll do the functional transformation like that because it's kind of fun to do. So I do this. So that was just using the extra. I still keep the where. I can still write a where. So that's still the same program. And then, of course, this H is actually the output of color, right? So I write that like this. I just put here color, but it's not the constant color, it's the output of color. Okay, and then I take color list and I put it here. And of course, it's not the constant color list, it's the output of colored list. All right, and then I look at that and I go, oh, that the head is the same, so I can put only one head and write it as a disjunction. And I have my type declaration, right? And then but the great thing is that I can run it. I can explore the inhabitants of my type. And then if I don't like that enumeration, great. So that's why we have our libraries. We can go to the search rule library and say, run everything breadth first. And then this gets much nicer, no? And then you can use your types as property generators, as test case generators, and then you don't have to invent property-based testing, which is, you don't have to invent many things. You
have, let's say, a random.
We have random, we have iterative deepening, we have all that stuff, yes. Yeah. We have random, we have iterative deepening, you can vary the parameters, and of course it's a world, what you can invent, but it's not so much, we use this stuff, no, and it can be, but it's what I'm trying to transmit is more the concept, how simple it is if you do it right, how many concepts you can incorporate in a, very simple language, it's all Prolog. It's all Prolog with a little bit of syntax and Ciao Prolog is very good at being able to define syntax and add syntax, and all these little things are expansions, but they're modular and it's really easy to do. So these are just let's say user level extensions, all the ones that you see here. Okay, so far so good. And what else? So I did the color list. So I can say, for example, this predicate. I don't know why today it wants to put the messages 2 lines up, but who knows. So for example, that is verified also, as you can see. So it's telling me color list, that it is X is the success, the success of M is a color list, which is fine. And if I put something else, and of course this is all running in the background, it's doing the incremental, it's doing, all these things, no? And then if I do that, then of course this is not a color list anymore, right? So I can also hover if I want there. So you see, it tells me false assertion because actually, you see, it's the type red A, but that's incompatible with color list and so on, and it has done that. So this is, with abstract interpretation, there's no types, no. It's all abstract interpretation. It's just a shape domain and the E-terms abstract domain doing that. All right. So if I go back to green, for example, so everything is ducky again, and we get our assertions proved. All right. And then, of course, we can have more complicated. We can have sorted, for example, which I'm writing like this. And then, interesting, we get a warning here. And the warning, if I hover here, is telling me that it could not verify the assertion because you cannot guarantee that when you call this property, this, which is a Prolog built-in, is going to be called properly. So it's warning you. You might call this with a variable, and then, of course, if I call sorted like this, it says yes, or if I do like that, it says no, fine. But if I call it like this, there it gives an error because it's calling x greater or equals than y. Now, of course, what I want there is not the Prolog built-in. What I want there is for example, well, first it doesn't know anything about that. It's telling me that it's illegal, the predicate undefined in source. But I can add CLPQ, why not? And then everything is ducky again. And then I can, things get much nicer, of course, no? All right, let me just do this so I don't forget. And now the last thing I want to show with this example, which is it's very small, it's very simple, but it's doing a lot of things. I hope you see that. Okay, so I put prop sorted because this is not really a regular type. It's maybe a dependent type or something. I don't know how to call it, but it's a property. We don't give so many names to things. They're just properties. Then, for example, if I call P that calls Q, then I get an error. And this error tells me false assertion because, and it says, well, how can it figure out that sorted that is not sorted? Well, it's not figuring out it's not sorted. What it's figuring out is that sorted implies list and that Q is returning red. I don't know if you remember that, but Q is returning a color. And then, of course, red is incompatible with list. Now, how do we do that? We do that because we analyze the properties themselves with other domains. So if you analyze the property sorted with domains of regular types, then you know what type it implies. So the success set is over-approximated by that type. And then if you compare it in the right way, you can prove that, that sorted is false. You cannot prove that sorted is true. For that, you would need a runtime test or a more powerful domain. Daniel has developed a domain that can prove sorted. But I'm not going to do that now. All right, so this is so much for this example. Let me go to another example. So yeah, a bit more evolving to a bit bigger programs. So for example, if I have this, sorry, it should be like this. Okay, so if I have this quicksort program, if I go to the beginning, it actually tells me a summary, no? And I know that in this module, in this program, I have two. So I have the number of assertions that went to checked, so that were verified, the ones that went to false, remember the picture, the ones that are in check. So here I have two in check, I can see them here, they're right there. This one, okay, and this one. And what it's saying is that it cannot verify that when you call arithmetic, it has the right properties, which are oops, yeah, okay, I should. So the right property is, one thing is that if you point with the pointer, the tooltip disappears. So the property is, it cannot prove that when you call equals less than, it's an arithmetic expression, not what you see on the top. So it should be an arithmetic expression. Now, how can we fix this? How can we fix this? Well, one thing is to use this module in another module, in another program, and then the other program will call it in a particular way, and we will infer if it's called properly. But if we want to, verify it on its own, then we can add an interface declaration. Now, none of this is compulsory. This is the important part. These are all voluntary. So I add an interface and I say that quicksort, when you call quicksort, the normal way to call it is to call it with a list of numbers and a variable in the first argument and a variable in the second argument. And then, this, at literal one, I successfully check this assertion. So I'm proving, remember that the arith expression part, that when you call these A and B, which are X and F, are arithmetic expressions. And the same here, no? I think I don't even need this probably. Right? Yep, exactly. So that's sufficient. Now I can do a lot more than that. I can do, for example, here I have added a lot of things. I said that, so what am I saying here about quicksort? I'm saying that if you call it with a list of numbers, it will return a list of numbers, it will not fail, and it will be deterministic. So no matter how you call it, provided it's a list of numbers, it will always succeed, and it will never give you two answers. I mean, it will give you only one answer, so it's deterministic, which is more or less exactly what a programmer wants of their programs, to catch errors and so on. And we're catching this, what have I done here? There. Oh, because I erased it there. So if I see here, it's telling me that it's verified. This assertion is verified. Verified assertion, blah, 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 blah. And anyway, so if I, here's maybe more interesting, I have other things, so all these assertions, like this. There you are. So all these assertions are verified. You see, these carets here mean that the assertion is verified. Doesn't give you a lot of noise if the assertion is verified. You know, we can play a little bit with this program. For example, if I take out these equals, I immediately get a problem. What is the problem? Who knows? What is the problem if I do that?
Can fail.
Can fail, right? Exactly. You know, so I get here. If I look, it says it possibly fails. You see there, the NF, the non-failure analysis is saying. So this by the way, these are the different domains. So the different domains, it shows this domain says that, this domain says that, this domain says that. You can have gazillion domains, and depending on the properties, it uses some domains or others. So it says it's saying possibly fails. So I cannot prove that it doesn't fail. Equally, for example, I can do this, and then I again get a problem, and now it's the opposite problem, is that it's not deterministic anymore, right? So that's very useful. Where else? And of course, I mean, there's all kinds of other, oh wait, so no. Still giving me a problem because I messed up. There you are. Okay. Are you getting better? Yes. All right. Oh, and of course you can do the usual things, you know, that if you like mistype something, all hell breaks loose, no? Because you start getting all kinds of things that don't match in different places. So the argument is that this makes Prolog very as useful as before for prototyping, but then when you want to coalesce it and make it reliable, you know, you can do it, and you can get the same kind of reliability and with properties that are hard, you know, that they're complicated. All right, more things. You can control the analyzer. There's this option menu, and you can do all kinds of things. You know, one of them, for example, that's interesting, is to turn on program point info. So I did this. This is turned on, and many other things. No, but if I analyze the program, and I'm doing it now in a different way, and I look at the output, I get all kinds of information. So I get the true assertions. The checked assertions are the things that have been checked. So for example, this one, just ignore it. It's because of the entry point. But like this one, for example, says that it's a computation assertion that says if you call it with a listed number, it doesn't fail and it's deterministic. That has been checked. So basically, our pred assertions here, these pred assertions have been translated into comp assertions and all kinds of assertions. All these other assertions, the true ones, are the ones that give the results of the analyzer. And the interesting point, perhaps, is this, that we also get information on program points. So if you see here, you have a clause, a quicksort clause, and then all these trues are the information at that program point from the analyzer, from the different domains. So for example, here we know just before partition, for example, we know that first and rest will be ground, and so on. Or here before, more interestingly, perhaps here before the greater or equals, where are we? There. So before this, for example, before this less or equal, we have lots of information, but one of them is, for example, that X is a number and that F is a number, and that's what allows us to, you know, prove that there's no problems, no? Because we have all this information, and we have versions and so on. Okay, let me speed up because otherwise I won't finish that line. So I'll go a little bit faster now because I want to go slow so that it's all very clear. So more stuff that is kind of neat. So we also have these things called modes, which, you know, if you're a Prolog programmer, you'll be familiar, but modes are just macros. So they are macros for assertions. So if we look at our previous this is pretty much saying the same thing. So this assertion, this assertion here and this is just a compact way of writing the same thing. So the modes basically are macros of properties, and they're defined like that. There's a language for defining modes. Say, well, my plus means that it will be non-var on calls and and whatever, or baron calls and ground on exit, you can define your own modes. So there's a library of modes. And you also have other compact, these are like Mercury style determinacy, and these will also get checked on the fly. As you can see, the little carets, so that works. Furthermore, since some people don't like assertions and they don't want their program to have some extra syntax, some directives, they don't want that. We can do other things. We can do. We can put the assertions inside doc comments, inside machine readable comments. So that is again the same. So you can say. This comment, which any Prolog, so this program, any Prolog program will read, and then the assertion is in a comment, so it doesn't bother, you're not adding any syntax or anything, so that also works. Okay. And so you see the little carets appearing here. More things. Quick things for this example. Also, I have to save, so it runs. So it gives me an error here. Now this is naive reverse, written with the functional syntax, but this is the naive reverse in Prolog that runs backwards and everything. But I'm saying that if you call it with a ground list in A and a variable, so you run it forwards, we will get a list in the second argument. A and B will be independent. We put that just for fun and so on. But that it doesn't fail, that is deterministic, that it terminates, but we also said, I don't know how I did that. Wait, I'll do it again. Okay. We're also saying that it's linear, and of course it doesn't like that at all. And it says, there. So it's showing that naive reverse is not linear, it's quadratic, so it's giving me a cost error, which is, so it's to show that it's not just types, it's not just, types are just one approximation. I can fix that, of course. I can say, and then it gets, verifies, so nice. And I can do other things. Like for example, if I say here that this is an upper bound, the length of A actually is not an upper bound, and I can even look, why is it not an upper bound? So I check, and it says, it's +1, because the base case, it's counting the base case. So it's telling you, no, it's the upper bound is A +1, length A +1. Okay, let's see, +1. Now. But okay, I like it like that, so I put O. Okay. I hope I get some smiles from you. All right, so a bit more complicated program. I'm going to run a little bit because I'm running out of time now. We started a couple of minutes late, no? So, yeah. So, okay. So this is a bigger program. There's a parallelizer, and then we get, lots of checks. Anyway, so it's basically the same thing. If you look here, for example, here annotations is reasoning about the data structures that are being built. It's basically processing programs and parallelizing them and so on. And here, basically, we're realizing that when it gets here, we're saying when you get here, phrase should be a variable. Info and phrase should be independent. Should not have pointers. They're recursive data structures, but they don't have pointers. Phrase would be, info would be a recursive data structure that doesn't have pointers. And on output, the both will be ground. And this, as you can see, is checked. And anyway, so this is a more serious program. But I won't spend time for that because I want to show something different. Yes, so one of the cute things is that this all runs on the browser. So, the whole CiaoPP system runs on the browser. And if we, what was I going to change? Yeah, let's just do the quick sort. I have a bunch of examples here. The same quick sort that we were doing. Yes, so we can, since we're familiar with this, we can load this in the playground. So this is the Ciao playground. So here you can, of course, load this program and then basically do quicksort. No, it does work. No. Now the good thing about this implementation, we've done several implementations of these kinds. Well, I say 33.2. I mean, it's going to be backwards now. So this runs here just the same as in the. But the thing is that here everything is running in the browser. So the whole Ciao system has come down, the analyzer, everything has come down, and it's running in the browser compiled to WASM. So you don't need any installation or anything to run this. And you can also analyze and check the assertions, as you see. So we get all the output, the checked, and so on. And here saying that the successfully checked assertions and so on. And if we mess up something like I don't know, we put here num to say something. I didn't turn on, sorry, I didn't turn on the flight check mode. Okay, so if I do that, hopefully it works. No, this num, yeah, so that was it's giving me an error, and the error is that, that is not a number. No, but if I go back to list num, why? List num. Yeah. It wants to go there. There we go. Now, so this should get fixed. If I'm syntax error. I'm asleep. List. List. Yes. Sorry, I'm asleep. You guys are asleep also because you didn't help me fix it. Okay. And now why is it list? No. This num why I'm still missing a parenthesis. You guys should, yes, now, yes. I'm asleep, I'm completely asleep.
After num there's a parenthesis.
After what?
No, after num is this num, comma, x.
Well, that's, yeah, but this is why, no? So why is it telling me? Well, I'm too stupid to fix it, but believe me that it works. What am I doing wrong?
Is sure?
Yeah?
Parenthesis, num, comma, delete this parenthesis.
Yes, so this one is wrong also. So I messed up this one also. You're right, yes, on below the same. Yes. I was too asleep, yeah. Okay, yeah, you see it works, It's not a demo, it's the real thing. Okay, so I see it works on the fly also okay. Now, last thing, so this is the last cool thing, is we also have, because we can run the analyzer and the verifier and everything, we can embed these examples. So you see, as you saw that we can actually run the analyzer by hitting that, and we can load it in the here on the fly. But for example, we can generate tutorials like this one. For example, this is a tutorial of Prolog tutorials, but also Prolog analysis tutorials. So this is, for example, a tutorial. I'm just going to go to an example here. Right, so here we explain the determinism domain and so on. And then we have this sorted insert program. And if I hit there, this analyzes, and then I can see that it says possibly not mutually exclusive, multi, so it's not, this is not deterministic, and maybe I want it to be deterministic, this sorted insert, since I'm calling it forwards and so on. So I'm basically missing a cut here. And then if I reanalyze, you see now it's detected that it's deterministic. But this is running in the document. The whole analyzer is inside the document. That's pretty cool. So if I reload it, you see, it goes back to the previous thing, no? Because it's all inside. Anyway, so that was the last thing. A couple of final remarks. Summary. We achieved what we wanted to achieve. Hopefully, we're still always improving, of course. Plus, we made Ciao Prolog even better. There's a lot of people involved in doing this. Many or some are here, and there's also a lot of people that worked previously on the system. So it's a totally incomplete list of where you have also John and so on. And anyway, so thanks for now.
Well, thank you very much, Manuel. We've time for a bit of discussion, questions. I saw Mikael first.
Yeah, so thanks for the interesting talk. So it's quite impressive what you have done, and I'm still do not know what are your, or whether you have any boundaries, for instance. I have a question. So if you have data structures and have predicates inside the data structures like search trees, and you want to prove properties of, if you have red-black trees and do operation on this, could you also cover this as properties?
So trees, we can cover trees, but if you have, you mean if you have properties inside the trees?
Inside the trees, for instance, that
well,
they have said that should be balanced and so on, and these kind of properties inside.
Okay, so let's, so you can write the property, of course. The property can be written. What is a tree with certain characteristics of the nodes or whatever. Let's say a tree that all the nodes are greater than 3. Let's say that, no? So you can write it in Prolog, of course, and then you can use it as a runtime test. So you could use it in assertions. You can always write a runtime test and use in assertions as a runtime test and put test cases and so on. Because I think the nice thing about the system, it unifies unit testing, test cases, property-based testing, static testing, and so on. Then the next question, so you can write the property for sure, and you can test it at runtime. Can we infer it at compile time? Well, that depends on what abstract domain we have. So for example, if we have trees whose element has sizes, that we can do because we have a size types domain that we use for the Pedro came up with we use it for the cost analysis, because we need to know the sizes of the things inside data structures. So those we can do. Can we do more complicated things? You have to develop an abstract domain, and that's why Daniel gave the talk yesterday here in LOPSTR about designing abstract domains, because in the end, I mean, if you have a complex property and you want to prove it, you have to work. You have to have, somebody must have written a domain, you or somebody else has written a domain that is capable of, the theory is capable of it. The question is, has anybody sat down and written the domain? It's still, the advantage is that you write the domain. So of course, what's the, we have? Testing we can do, no problem. They're improving is they're improving, but you have to do it by hand. You have to work at it by hand. We're trying to find the automated point in the middle, the farthest we can go with total automation. So there's a price to pay, which is to develop domains. So that's it.
Thanks for a really cool talk. So in the data log for static analysis world, people are trying to make things incremental by making the whole data log engine incremental. How specific is your incrementality here to the analyzer part, or could it also be applied like to the whole Prolog program in general?
To the execution of the Prolog program, no, I don't think so. I mean, it could be done, but it doesn't work right now. But the analyzer can be used. I mean, the analyzer is, in reality, the analyzer is a Prolog system. It's a Prolog system with tabulation. So you can actually run the programs in the analyzer. So in that sense, yes. In that sense, you would have a super optimized with tabulation. We also have tabling in the Prolog. So the tabling you can do. I don't know. Jose maybe has a better answer.
You answer it.
Oh, sorry.
I think there are some papers from XSP guys,
Yep.
XSP Prolog about tabling incremental.
Oh, yeah.
Yeah.
So the XSV Prolog system that implements tabling, they have some papers about the incremental tabling that connects, as Manuel said, with the fixpoint, because our fixpoint is a tabling.
It's an OLDT,
strategy,
so it's a tabling resolution prover. So in fact, I mean, it's exactly the same algorithm. We discovered this. We published the algorithm, the incremental algorithm for the analyzer and for the XSV system in the same conference, in the same SAS, if I remember well. So we came up with it. I think we come up with it a bit earlier, but yeah.
Other comments? Yeah.
Okay, you say that, well, this is for Prolog, what you showed us, but it can be applied to other languages via a translation from the language to constraint horn clauses. So I was wondering, first, if there are, let's say, realistic languages that get translated to constraint horn clauses, and for runtime checking, can you do something? I mean, you get, let's say, the verification through constraint horn clauses, and then the residual checks are done at runtime in the language, in the source language,
Correct.
Or something like that.
Yes.
I don't know. Is that possible? Can you do that?
Yes, yes, a very, very good question. So let's analyze the parts. I mean, so you can take the original language. I mean, actually, that's why I put this example here. No? So you can take the original program. This gets translated into machine code, LLVM. Then we translate the LLVM to horn clauses, analyze the horn clauses, and we reflect the results back on the source program here. Now we haven't done, so we've done that for Java bytecode contracts, for Tezos contracts, for Michelson. We have done it for XC, for machine code out of C programs. These are prototypes. They're not production systems. The prolog system is pretty much a production system nowadays. These other are prototypes to show feasibility. Now we have done this part of injecting the results back on the source code. We haven't done the on the fly, but it's engineering. I mean, it can be done, no? Now, the interesting question, but you went further, and it's a very interesting question, which is, now, if I write the properties in my source language in C, let's say, I run an assert in C, then I can, of course, I can do all these tricks of analyzing that, because I can translate the assert to, if I know how to translate prolog to horn clauses, I can translate the runtime assertions, the ones that run. Those I can translate to properties and to horn clauses and use them in verification and so on. So I think some part of it could be done. What is harder is if you write a property in, let's say, for example, terminates or cost, you have to write the runtime checker. You have to write it in C. But we also have to write it in prolog, right? Because we don't have, it's not like you write some magic bit of prolog. No. I mean, for example, for the terminacy, you know, that's a check that is built in, because we basically look at, the efficient way to do is to look at the choice points in the stack, in the choice stack and so on. So partly. Great question. Yeah.
Yeah, one last question then.
Thanks for the exciting talk, Manuel. So just kind of building on the last question, right? Like, if I'm trying to design an analyzer for a new language, complicated language, JavaScript or so forth, then I need to build that translation from JavaScript to constraint horn clauses, and that's a lot of the challenge of sort of encoding the semantics. So I don't know, how hard is that, and is there some sort of gradual development process that could allow me to sort of prototype more quickly kind of analyzers for new languages?
Okay, so we didn't get into how you do it. You could ask John, who's the master on this. I mean, so there's several ways to do it. There's one standard mechanical way, proposed by John, is to you write an interpreter and you do the Futamura projection thing. So you write in horn clauses an interpreter of the language, and then partially evaluate the program. So that's the cool and right way to do it, because you're sure it's correct. The translation is correct. Then there's, okay, so you do the Futamura projection by hand and basically have a translator, based on what you see from your interpreter. Because in the end, you eliminating the interpretation loop, you can also do it by hand if it's too hard. Although John has had great successes in doing that automatically. But then, and there's a whole thing about the small step and big step, and I mean, we'll get into a humongous area here. But I should say that the way that we do it, because a lot of people do the small step thing, which is to, to kind of describe transitions in the states of the imperative program. But we basically use the fact that Prolog can run imperative programs. So basically, we translate the imperative programs to Prolog. So we use. That's a bit harder to understand, but basically, if you have an analyzer of Prolog, you can analyze any program. It's not, there's nothing that Prolog doesn't do. It has assignment also, you have to deal with it, and it has dynamic modification of the program. So if you have a dynamic language like JavaScript, you're not any worse off than in Prolog, because Prolog has a certain retag and can change the program on the fly, and we have to deal with all that. So it's as complicated as it gets. This is why we have always worked with Prolog, because we think it's kind of a superset of what you can possibly do in a language. You know, it has all the complications. It has pointers, which normally you don't have in functional programmers and so on. It has logical variables, which are pointers, and they can have aliasing, so you have aliasing analysis and sharing analysis. You have everything, all the complications that you think. If you can do it for Prolog, then you just translate and analyze. That's at least our theory, no?
I could just add that you can use the compiler also. I mean, you translate from the intermediate representation generated by the compiler. So a lot of the work of handling the source code could be done by the compiler, and then you translate the control flow graph or something and into horn clauses. But it's a long story.
It's a long story. So LLVM, you know, like I said, this was done that way. This was done with the LLVM compiler. So you take the LLVM representation, and that's what you translate into the horn clauses.
Let's take the discussion offline from now on. And
right. We have another talk, yes.
And for a very interesting and stimulating talk. Thank you.
Thank you.